Good afternoon, everybody. Welcome to our first session this afternoon. I'm Andy Purvis, Director, Sustainable Manufacturing with the World Steel Association, and I'm delighted to be able to chair this session. This morning, we talked about energy a lot. This is session 2, and we're looking really at the other side of the coin in terms of steelmaking. It's a matter of energy and reductants. So this session is focused on fuels, reductants. We'll be looking at hydrogen, biocarbon, CCS, carbon recycling technologies, all, I think, really important pathways in our transition. And we've got a great lineup of speakers. So I will encourage all of our speakers have 20 minutes to make their presentation, and then we'll have 5 minutes of questions after each one. I ask each of my speakers to be disciplined in time, and we'll keep things on track. So we'll make a start now. I'll welcome my first speaker. There he is, Joachim. Please come up, Joachim van Steel. So Joachim has been is with Linde, and he's been in the industrial gases industry since the 90s. Worked across Asia, South Asia, India, China, and has been in Linde. Really focuses on the use of hydrogen and industrial hydrogen. And he'll be talking this afternoon about the full-scale implementation of hydrogen as a fuel. Joachim, please come up, and the floor is yours.
Thank you very much indeed, Andy. Very good afternoon to you, everyone. Great pleasure to be here and talk about hydrogen, the buzzword hydrogen, and use of hydrogen as a fuel. A lot of the discussions about hydrogen in the steel industry is about hydrogen used as a reducing gas, of course. But there is another part of the steel industry where it can be used as a fuel. And I will put that into context. I will move rather quickly through a number of examples, because I will talk about not what we will do so much, but what we have done. And I'm very proud of that. We have some reality checks and showing what works here. From our perspective, when at Linde we are looking at hydrogen since many, many years, for 50, 60 years. Hydrogen is one of the offerings from our end when it comes to decarbonization. But of course, it's not the starting point. The starting point is energy efficiency. Of course, we should start there. And we could look into other means as well. That includes carbon capture. That could include syngas production, for example, from waste. Hydrogen, we operate 230 hydrogen plants as of today. More than 80 of them are actually electrolyzers. The rest are SMRs and ATRs. We have been running tests with hydrogen across many of these hard-to-abate industries over the past 6, 7, 8 years, steel among them, but also cement, for example, and glass industry, non-ferrous, and so on. It's quite tricky to carry out full-scale tests because you need to bring in the hydrogen there. We've been running up to about 5,000 cubic meters per hour. We've been running for 2 weeks with the 3,500 and so on. It is difficult, but the results have been great. Traditionally, again, it's about reduction. It's about use of hydrogen in a short-term perspective, for example, injecting hydrogen into a blast furnace, and there are a lot of discussions, of course, about using hydrogen to a large extent in DRI production. And today it's about reform natural gas, so it's not that big a step in a way there. But what is worth noting is the scale required here when it comes to the hydrogen supply. The huge amounts. And if you look at the DRI plant of a typical scale, we might need a 1 gigawatt electrolyzer. And those are not off the shelf today, so keep that in mind. However, it worked out fine. We've been involved with trials in blast furnaces. Here are 2 examples from that, what we've done with the Cleveland Cliffs in Chicago and with Erdemir in Turkey. But that has been done on a level that's equivalent of 1 kilogram of hydrogen per ton hot metal, which is a fraction of what you maybe recall from the previous slide. Works fine, all good. So that was about that part of the reducing gas. Now let's move into the use as a fuel. That is in the melting operations, that is in the heating operations. We start with reducing the need for energy. That is the starting point. And if we can do that by going from air-fuel combustion typically to oxy-fuel combustion, we can do fuel savings on, let's say, 30% or something like that. If we can do that in such a way, so we can also be ready to use hydrogen when there's a viable supply, that is the perfect pathway, I would say. Oxy-fuel installations across the industries, we as a company have done about 900 of those, the majority of them in the steel industry. So this is no news for us. What does it mean? Many people say, oh, this is a strange, it will have a lot of implications of the processes. Well, the big step going from air fuel to oxy-fuel has been taken at many occasions. And of course, it has an impact on the furnace atmosphere, for example, where we go up to have the products of combustion that are practically only CO2 and water vapor. However, what is interesting to note here also is that use of oxy-fuel combustion is very good for carbon capture, as we reduce the flue gas volume by, say, 75%, and we increase the CO2 concentration. So, looking at the toolbox we have, it can also be combined in that way. And if we go the second step into use of hydrogen, we need less hydrogen, simply. Okay, what happens when we combust hydrogen and we do hydrogen oxy-fuel then? To be efficient, to fire less of hydrogen or less of fossil fuel, we do oxy-fuel combustion. We started big campaigns with this in 2018. Here are some pictures from, we have 4 tech centers in the world. 3 of them we do hydrogen combustion. This is from Munich, actually. And down to the right, there you see the 100% oxygen, 100% hydrogen flame. Beautiful. It's water vapor radiation, pinkish. Works fine. Here you can see what happens when you blend in hydrogen into the oxy-fuel, moving from 100% natural gas to 100% hydrogen, and see this in the various steps. Simply, this works perfectly fine. Another example of this photographs from these tests, again, blending. A lot of people talk about blending, and it's a good way to increase your understanding for it. A little bit of thermal images, 100% natural gas, oxy-fuel to the left, 100% hydrogen with 100% oxygen to the right. We get a little bit better heat transfer also, as you can see in the diagram. So, in simple terms, box is ticked. This works. And we can conclude that also from our experience using hydrogen and oxygen in the glass industry, for example. So we can blend in all the way up. However, what is worth noting is that we should be very careful if we blend in with air-fuel combustion, normal air-fuel combustion, because then we could have a negative trade-off, creating a lot of NOx, saving CO2, creating NOx. That we don't want. So we have been working with this, and I can tell you that the good story is that we are not increasing the NOx. We are decreasing NOx, we are decreasing CO2. It's also worth noting that when blending in, we talk about percent, and that is volume percent. If I blend in 50% hydrogen into the natural gas, I have 50-50 mixture. The impact on the carbon footprint, providing the hydrogen is 100% zero carbon footprint, 100% green, so to speak, is a little bit more than 20%. If I would do only a conversion from air fuel to oxy fuel, I would probably save 30%. One of many technologies is the cojet technology that we introduced in 1996 to become industry standard in electric arc furnaces. We had tested this out in full scale. It works perfectly well for the flame envelope of the oxygen injection jet. Not only are we saving on the fuel, but we are also getting a longer oxygen jet. It travels a longer distance, so it's a process improvement. Another example of use of hydrogen in the steel industry we tested in full scale is at continuous casters. This is a picture from a Bloom's caster where we have been running 100% hydrogen, 100% oxygen cutting. It works extremely well. It works so well that we could increase the cutting speed, and despite that we were reducing the power. I think that this is an implementation and use of hydrogen that is on a smaller scale, but is a way to get used to operate with hydrogen that will come in the next years. We don't have it in full-scale operation yet, but I think we will see that actually already next year. That was examples of when we are cutting, when we are melting. When we go into heating, we talk about another type of oxy-fuel combustion. We talk about flameless combustion, not conventional. So we create a flame cloud instead of a very sharp flame. This is what we apply when we heat something. That could be a ladle, or it could be a piece of steel. For ladles, we have tested this out full scale. We also have smaller installations up to 7 tons running with 100% hydrogen as a fuel using flameless combustion. So this works. It's more of a supply issue. And let me give an example from this part of the world where we see something new happening, and that is use of flameless oxy-fuel to heat tundiches. So I'm very, very happy to reference that we see use of new technologies in the ASEAN countries here. This is from our great friends at Yasumitsu Steel in Thailand, where we have the world's first two systems with this. And this is then a possibility to use hydrogen going forward as well. Now, reheat furnaces. We've been working for a number of decades with converting reheat furnaces into use of oxy-fuel combustion of various kinds. To date, we have done 190 installations across the world. In the past, this was mainly driven by getting more tons out per hour in existing furnaces. Lately, the focus has been on fuel savings. And this year, we've done 4 or 5 furnaces, actually. We just started up 3 furnaces at Taigang Tisco in Taiwan, and we see more and more of this coming. So what will happen when we heat a material using hydrogen? Flame was okay. That worked. No increased NOx, actually a reduction. But what will happen if we start heating material, heating steel? So back in 2019, we went together with a number of steel companies and made tests in lab scale in Sweden, in our tech center. They brought their own material. You see, this was SSAB, Alema, Ovako, and Outokumpu. So it was alloy steel and stainless steel and so on. We made this test running with 100% hydrogen in the same fashion as running with the heating curves with fossil fuel. They made the tests themselves, checking if there was any hydrogen pickup, increased scaling, decarburizing, etc., etc. And we got together, and it was concluded they couldn't tell the difference, which was a great result. There was no negative impact on the material. And one of those participating companies, Ovako, decided to go ahead together with us in 2020 to make the world's first full-scale test in the Hofors plant. And we were heating then 25 tons in the soaking pit furnace, as you see there, in March 2020. And that went in this, everything, all operations the same as in the other furnaces. A batch there is coming from the EAF is 100 tons divided into 4 pits, one of them operating with hydrogen, the other 3 as a reference. Couldn't tell a difference after rolling all the testing and so on and so forth. And it was then decided that after this world first, let's make it a real world first and make it in absolute full scale. So early last year, Ovako started operating this system, 100% hydrogen, 100% oxygen, across all the pit furnaces there. The hydrogen comes from an alkaline electrolyzer, 20 megawatt. The electricity is 100% green. It's a blend of hydropower and wind power that is feeding it. The same goes for the oxygen that is supplied. So both the hydrogen and the oxygen is 100% zero carbon footprint. They've been operating since early last year, and the experience is fine. There is no negative impact from this. 500,000 tons, 500,000 tons have been produced in this way. This is a full-scale permanent installation, and it's running fine. Continue to run there. This is a real benchmark and introduction of hydrogen as a fuel for reheating. We worked with Ovako for a number of projects over the years, and over the past 2 years we converted some of their continuous furnaces to 100% flameless oxy-fuel. Examples from Imatra and Boxholm, Imatra in Finland, Boxholm, Sweden, and we made those furnaces hydrogen ready. There's not hydrogen available there today, but as soon as that is the case, we can start operating these furnaces also with hydrogen. And we had already very good fuel savings. First we fire less, then we fire clean. So in Boxholm case, we even reduced the fuel consumption by 50%. Another project we are doing is with Gerdau, and one of their mills in the US, and next year we will do the full-scale testing in the walking beam furnace that you see on the picture there. So let's do a quick number crunching. This is a back of an envelope calculation that you see there, and I highlighted some figures. We can discuss numbers and we can discuss decimals and so on and so forth. But the question that comes, if you have a huge reheating furnace, and let's say it has an air fuel power of 100 megawatts. That's a huge one, sure, but it's easy to calculate when you start with 100. Okay, if I would convert that into oxy-fuel combustion, I would reduce the power by 30% typically. And then I could, of course, play with putting in hydrogen with the air fuel. I could blend in hydrogen with the air fuel 50-50. I could do the same with the oxy-fuel and so on and so forth. And then we can start thinking of what are the reduction in carbon footprint. I'm here comparing the reduction in carbon footprint between the air fuel and the oxy-fuel, and also look at what is the power that we need for the hydrogen, how big electrolyzer in that case, and how much we can reduce that one. And of course you can see that it's better to use oxy-fuel than blending in 50% hydrogen with air fuel. And if we use oxy-fuel, we need smaller power for supplying it, substantially smaller. So we talk about 100 megawatts instead of 150, right? How does this look like if you take now a step forward and 15 years from now? Some of you would react to the figures that I put here because they might be lower than what you expected, but I try to be realistic. I think that for DRI, about 2.5 million tons of hydrogen will be used in 2040, looking at what is reasonable progress to come. There will be some use of hydrogen in blast furnaces, but there will also be use of hydrogen as a fuel, and that could be in those applications that I have showed here in my presentation. If I look at this as a whole, 15 years from now, there might be around 4 million tons of hydrogen used in the steel industry globally. 70% for sure, the bigger part will be used for reduction, but about 1/3 will be used as a fuel, which is not very much discussed. What are the obstacles here? Well, one of the big obstacles is that everyone thinks that hydrogen will be cheaper, and that stops it from becoming cheaper. I call it the catch H2. As long as people expect the hydrogen to become cheaper and do not commit, we cannot scale up the hydrogen supply. Of course, there's also a determining factor, the price of electricity, talking about electrolyzers. In most places in the world, if you look at the total cost of hydrogen, somewhere 50 to 70% is the cost of electricity. However, we need to go up to a bigger scale than we have today, and to be able to do that, and we and other people are absolutely fine to do the investments, but we need to have the off-takers to sign up for that. And if they just wait for the hydrogen magically to become cheaper by itself, we won't get there. This is the catch H2. Alternatively, we could of course supply the hydrogen based on natural gas, using an ATR or an SMR for that sake, but an ATR nowadays, and doing that together with the carbon capture. We've been looking at that at many places, and just throw a number here. If we would take natural gas from Norway, bring that to the Netherlands or Germany, and make hydrogen out of that, we will have a carbon footprint of between 1 and 2. Probably closer to 1. If we would take grid electricity in the Netherlands, we will have a carbon footprint of 5. So the blue is greener than the green. And the scale is there already. I have mentioned we have a project there in Canada, actually, where we are with Dow Chemicals, that we are on the same scale as a 1 gigawatt electrolyzer, but we are making it from natural gas. So, just to conclude, we can use it, the hydrogen, both as a reducing gas and as a fuel, but it's a big difference in scale of the implementation. We need much smaller scale of electrolyzers, so it's much more accessible. We can save fuel today. We can implement the use of hydrogen much quicker if we do it with the fuel, as a fuel. That could be for cutting, that could be for melting, that could be for reheating. And we have the proof already, it works. It's not a question of if it works or not. It works. It works. 500,000 tons already being reheated. So we can go ahead with this, we can take this to the next level, so on. The problem is rather to find a way to have a viable supply of the hydrogen. We know how to use it. We know that we can do it. We know that we get the results that we want. No increase in NOx. We get the same steel quality as before. Hydrogen is great to use as a fuel in the steel industry, not only as a reducing gas. Thank you very much.
If anyone has one, please raise your hands and we'll get a microphone to you as best that I can see you.
I'm around here, so.
I have a question.
Yeah, please.
I'm just thinking about management of change when you move from oxy-fuel to oxy-hydrogen. How much of a challenge did that prove to be in terms of safely transitioning the infrastructure? Thinking valves, pipework, those kind of things?
We don't see any challenges in that. So we have a hydrogen business in Linde that is $3 billion. We've been operating hydrogen for more than 50 years in various applications. We don't see an issue at all with that. Hydrogen is reasonably safe. Compared to heavy gases, it's much safer. So we need to be careful, of course, so it doesn't ignite, but otherwise it just evaporates. And yeah.
So you need someone who knows what they're talking about to support you.
Yep. Okay.
Fantastic. Thank you, Joachim, very much.
Thank you, everyone.
We will move swiftly on to our next presenter. Please come up, Mr. Leo LUO, who I will quickly introduce. Mr. Leo LUO serves as Chief Researcher for Low Carbon at CITIC Pacific Special Steel Group and works on sustainable low carbon technologies and products based on life cycle assessment methodologies. And today he'll be talking about innovation practices in coupling application of new advanced technologies of hydrogen, oxygen, intelligent combustion. Mr. Leo LUO, are you going to be speaking in English or Mandarin?
English.
English, okay, all right. You have 20 minutes. The floor is yours. Thank you.
Thank you. Good afternoon, everyone. This is Leo LUO from CITIC Pacific Special Steel. I'm now handling the technology work concerning climate protection. I'm really excited to be here at this conference and have the chance to tell all of you our technical solutions for greener special steel. What I'd like to share with you today is the innovative company of hydrogen, oxygen, intelligent combustion for nearly zero carbon dioxide special steel. Before diving to the main talk, let me make a quick comment for our company to tell you a bit about our company. CITIC Pacific Steel is a highly specialized special steel manufacturer in China with 9 subsidiaries. And the headquarters of our company is based in Jiangyin City, Jiangsu Province, around 2 hours by car from Shanghai. And all of our subsidiaries lay out along the Yangtze River and the seaside. We're also a public company listed in Shenzhen stock. As one of the leading steel manufacturers in the world, CITIC Pacific Steel is always committed to climate protection and implementation of our customers' expectation. Low carbon and sustainability is our core strategy. Early in 2022, we have issued a decarbonization roadmap worldwide with a vision: green manufacturing, manufacturing green. Green manufacturing green is not only a vision, but also an innovative action program supports our climate protection. It contains as 3 minutes: green manufacturing green manufacturing technologies, green manufacturing products, and manufacturing green products. Generally speaking, we try to reduce the carbon emissions in our own plants with leading-edge technologies, while to help our customers and the users to reduce their carbon emissions with our advanced products, and help the clean energies to reduce their cost and upgrade their equipment. Finally, supports the manufacturing green. In July last year, in the World Steel Association Conference, we initiated scientific and sustainable decarbonization while cooperative innovation to push the carbon emissions and economic benefits to go hand in hand. So now, let's return to the topic of the reports, 4 chapters for you. The first, the project's background. It's undoubted that climate change is the biggest threat modern humans have ever faced. Low carbon and sustainable development is definitely the way forward in the future. According to the analysis from Columbia Business School, steel sectors Scope 1 and 2 account around 10% of global emissions. Furthermore, as the basic material, steel supports the development of advanced equipment for low carbon transition. So all in all, the steel industry is super important in the global low carbon transition, where steel players must take the heavy responsibility of the climate protection. You know, ever since the 20th centuries, the modern steel industry has come a long way. It makes huge leaps in quality, cost, and efficiency, turning steel into a go-to material. But the technologies based on the carbon oxygen reactions make a big contribution. But starting in 1980s, people started waking up to the climate change and takes it more seriously. So the carbon oxygen reactions became also the big problems. As you're aware, it's the main cause of high carbon emissions. So it's essential to improve the traditional metallurgical theory and the technology aim for the low carbon. Replace the carbon with hydrogen is the key for the steel industry to achieve the nearly zero carbon manufacturing. Within clean energy and the hydrogen technologies are the key supports. So we examine the whole greener hydrogen chain from the production, storage, transport to the end use, and finally identified a key R&D project list focus on the hydrogen metallurgy technologies, hydrogen combustion, as well as the special steel for the clean energy and the hydrogen industry. Right now, hydrogen metallurgy still faces the theory and the cost challenge, as you know, so it's not ready for the large scale use. But the combustion is the center of the steel manufacturing. Efficiency and high quality heating is crucial for the performances, quality, energy conservation, and environmental sustainability for special steel. So we focus on the hydrogen combustion technology to cut down the carbon emissions while boosting the economic benefits, decarbonization benefits, and the product qualities all at the same time. Now, let me introduce our answer, combustion company innovation. Replacing the fossil fuels to hydrogen can achieve zero carbon combustion, but we think zero carbon combustions doesn't mean zero carbon productions. It's necessary to meet the requirements of safety, efficiency, and low consumption at the same time. And it's need to ensure there is no adverse effects on the process and the quality of the special steel. So therefore, while conducting research on individual technologies such as hydrogen combustion behavior and control method, the industry verification and multiple technology coping should be carried out. For this purpose, a three-level R&D system has been established, covering the basic research, single-point verification, and multi-point coupling. Hydrogen. As you know well, hydrogen has a high energy density and low consumption, and there's no carbon emissions. So the hydrogen is the core, we think it's the core stone of zero carbon production. But hydrogen is flammable, explosible, and proven to leakage. It's characteristic like the faster burning speed, high temperature, and the flameless, and the hydrogen embrittlement brings a huge risk for you to use. So first of all, we did a thorough research on the combustion behavior of the hydrogen and try to develop the special banners to make sure the combustion is safety and controllable and reliable. Oxygen-fuel combustion. As you know well, the oxygen-fuel combustion can improve the burning efficiency, reduce the fuel consumptions, and also can cut the emissions of the pollutants like the nitrogen oxygen. We think it's a multiply for efficiency and environmental protection. But under the low gas full gas conditions, there are maybe some challenges like the low burning life, uneven heating, and it's difficult to control the atmosphere. So we focus on we want to update the burning design and develop the new control system to master this good technology. Intelligence. If the ultra-full combustion and hydrogen combustion presents the body and heart, we think that the intelligent combustions should be the brain and the nervous system to breathe life to them. Software and hardware work together to make up this full intelligence combustion system. Turning it into account of living wholes can sense itself and make design get better over time and even evolve. Through systematic integration and intelligent regulation, the three combustion technologies are deeply coupled to achieve a qualitative transformation from complementary to synergy. So the third, the project results. The project have completed an engineering study and verification for action for combustion, intelligent combustion. This is a pilot project in one of our subsidiaries, TPCO in Tianjin, for the reheating furnace for the seamless production. And this is a pilot project for intelligent combustions in Jiangyin Special Steel Blast Furnace. As you can see, we achieved the good results. The furnace temperature average reduced by around 85%, and substandard molten iron rate decreased by around 23%, and the coal consumption decreased by around 90%. Daya Special Steel, one of our subsidiaries in Hubei province, completes the projects, company application of the multi-combustion technologies for the buried steel, very key products in steel industry, based on the EAF plus 100% green energy and 100% recycled steel. We use the ASM method to evaluate the projects in Vext, just for Scope 1 and Scope 2. So, as to the economical model with the industrial byproducts hydrogen, the process carbon offset carbon emissions reduce around 80%. Product carbon dioxide emissions, that means PCF, reduced by around 30%. The cost saving by around 35%. For the net zero emission model with green hydrogen, the partial carbon emissions can reduce zero, and the carbon and the PCF can reduce around 50%, but the costs have a big increase, around 45%. Combustion quality performances. The heating rates increase around 22%, and the temperature uniformity have good performances. The amount of the iron oxygen scale reduced around 31%. Finally, I would like to say thank you to our partners, Jiangyin Special Steel, Daya Special Steel, Tianjin Steel Pipe, as well as German Linde and Nanjing Ningpu, CITIC Energy Conservation, CENTRO Steel Thermal Energy Design Institute. Thank you for your help. And sorry, so thank you for your information.
So I look around. It's actually very hard to see, especially at the back. I have a question. I think, in general, it's great to see this. We're moving from what we're going to do to examples of where we as an industry have delivered and have done stuff. What advice would you give to another organization looking at using hydrogen within their process from your learnings? Is there any advice that you would give another company who are looking to use hydrogen? What was your main learning from using hydrogen?
Hydrogen. Okay, yes. So for the, as you can see, we set two models. One is use industry production by hydrogen, just for the economical consideration. And we also use pure hydrogen, just for the technology verification. Just now, one of the person have said that now it's difficulty to fulfill the price, the cost for the green energy. So maybe in the future, when the price, the cost is available, we can use it. Currently, we running the projects with the production by hydrogen.
Okay. Oh, we have a question here. Do we have a microphone?
Thank you for the presentation. You mentioned 20% CO2 reduction in the blast furnace process. Are these only calculations, or did you achieve these results in the real operation?
Sorry. I make some problems to your questions.
Okay, try again.
Okay.
You mentioned 20% reduction of energy, CO2 in the blast furnace process. Are these only calculations, or did you achieve these results in the real operation?
I'm so sorry, it's not for the blast furnace, just for the reheating furnace is the only process, yes.
Yeah, are these results, is this a result of calculations, these savings of energy, or is this real operation?
It's verified in our own plant in Daya Special Steel. Yeah.
Okay. Thank you.
Thank you.
Fantastic. We move to our third presentation. Is our speaker around, Mr. MAJUMDER? Excellent. There you are. So, Mr. MAJUMDER is coming to us as General Manager of the Sinter plant within SCHÉELE, with India, at Durgapur Steel Plant. He has over 30 years experience within SCHÉELE, working really across the process route, from the Sinter plants, in maintenance, the steel melting shop. And he's going to be talking us today around a slightly different angle. We've heard about hydrogen. We're going to move to biomass. We're going to hear about sustainable decarbonization of iron ore sintering by replacing coke breeze with bamboo biochar.
Good afternoon, everybody. I am Indranil MAJUMDER, CGM Center Plant, Durgapur Steel Plant, Steel Authority of India Limited. I am going to present our work on this sustainable decarbonization of iron and iron ore sintering process by partial replacement of coke bridge. This is a basically joint effort exerted by our R&D team and the works division, that is the steel plant. So this joint venture has been done by R&D RDCIS Ranchi, and they have done or conducted a lab scale trial and that has been implemented. Basically, trial, the one idea is to cropped up, and that has been implemented. Whether that lab scale trial is actually going to give a result in the actual scenario or not. So we accepted that the trial result to get it implemented in our plant scale application. So going forward, this will be this framework of presentation. That is a SCHÉELE network. So what is SCHÉELE in India? Actually doing with the Steel Authority of India Limited, a public sector undertaking under Government of India. Then the Sintering basics and role of coke bridge. Then biochar as a substitute, what is the idea is all about. Then characteristics and comparison, that is the different parameters of this biochar, and the comparison of this benefit of biochar or the contribution of biochar in the context of that coke bridge utilization. And then a lab scale experiment, what we have done in our lab scale to introduce biochar as an alternative fuel as against coke bridge. And then plant scale trial and that pellet dissection, then what are the result we have got after usage of biochar by partial replacement of coke bridge, and what is the sintering process has progressed, and what are the result, the quality of sinter we have got after this replacement, and then the trial result and future scope. Now going forward, the SCHÉELE network, we are having 5 integrated steel plants all over the India under SCHÉELE, and our Durgapur steel plant is located in India, the eastern part of the country, and our that R&D center is also at the eastern part of the country. It's 300 kilometers away from that Durgapur steel plant. Now this is sintering basics and coke bridge. The sinter, what is sinter? The iron itself, the iron ore fines, which is basically the most of the fines generated by the mining of lump ore, then that fines cannot be rejected. So we used to use that fines to charge into the blast furnace, but as fines form, it cannot be used in the blast furnace. So we used to agglomerate it to form a lump and charge in the blast furnace. Now this is the outline, this is the flow diagram basically of a typical sinter plant. There is the iron ore fines basically mixed with different kinds of fines material like flux, that sinter return, then the fuel. And that the whole combination of this mix is called raw mix, which is the green mix charged to the sinter machine. Then once it is charged in the sinter machine, the flame is applied to burn the fuel on the top of the sinter machine, and it is gradually progress and sintering happens. Now coke bridge is conventional solid fuel of sintering, and these are the typical, though first we used to evaluate what is the role of coke bridge and what will be the role of biochar. Basically coke bridge is used to give heat. Apart from is the property of reduction of iron ore. Now, we have evaluated the coke bridge in terms of its heating heat value used to impart in the process of sintering. So these are the chemical reactions we have analyzed, that the heat value the coke bridge used to impart in the process of sintering. Now, coke bridge is conventional solid fuel, and this is the basically heat value we have calculated. And the heat value of that calcium carbonate, the coke bridge utilized for heating of the iron ore fines mixed with flux. Flux means in order to maintain the basicity in the blast furnace, we used to use crushed lime -3 mm size and dolomite into the iron ore fines mix to form a raw mix. And for heating value of the coke bridge is utilized the heating of iron ore fines in pure form, as well as for heating of these fines material in the form of lime. So these are the heat used to impart to that heat of calcium carbonate, heat of the dolomite. Then the heat is used to reduction of the different forms of iron oxide. Now, biochar as substitute as alternate fuel. So this biochar is considered as a carbon-free resource. Basically, biochar, what we have considered in our experiment is the use of bamboo biochar. My next speaker will explain you what is the my co-speaker. Actually, I will like to invite Mr. Dhara. He is, and I would like to share the stage with them, as because this is a collaborative effort exerted by our steel plant as well as our researcher team. So I would like to have Mr. Dhara with me as a co-presenter. He will explain then what is the use of biochar and why we have considered biochar as alternate fuel by substituting the coke bridge. Now, this is the Government of India roadmap for decarbonization. So, this is a different year on year. The sintering process, the steel industry is the emitter by, say, 10 to 11% of total carbon dioxide equivalent in the global industries. And in Sinter plant, this is the second highest emitter of carbon dioxide equivalent after blast furnace. In India, we are now operating with a carbon dioxide equivalent emission in the range of, say, 2.4 to 2.5 ton per ton of crude steel. Now, as Sinter plant, as the second highest emitter of carbon dioxide equivalent, it is emitting approximately 0.46 ton of carbon dioxide per ton of crude steel it's produced. Now, this is the biomass to biochar. Basically, biochar is a stable carbonaceous material produced by heating organic waste like bamboo and wood waste in an oxygen-free environment through pyrolysis technology. Now, biochar is theoretically suitable for sintering application. Now, what is biochar? Biochar is the calcium, burning of bamboo in low or absolutely free oxygen environment. So, biochar is having a higher calorific value. It is almost having a, say, a 7,500 kilocal as against coke bridge of, say, 6,500 kilocal. So, in terms of calorific value, bambuchar is having higher calorific value. Now, this characterization and comparison, what we have done in the analysis part. This is the proximate analysis of that biochar versus coke bridge. We have shown that in the first column it is coke bridge. The proximate analysis, coke bridge is, the data is like that. And if you come down to the last row of this, gross calorific value, the coke bridge is having 6,000, and as against bamboo biochar, what we have chosen for the alternate use, that is 5,900 or, say, 6,000. So, it is almost equivalent to the coke bridge. Now, the characterization of biochar and versus coke bridge in sintering, that is the combustion rate. Coke bridge is very slow and steady. Biochar, as because its flame point is very less than coke, so it's burns short. And these are the comparison what we have predicted and analyzed and got the result. Now, the lab scale experiment what we have done in our R&D, Mr. Dhara, if you can come down.
Good afternoon. So, first of all, what we have, MAJUMDER sir has shown that in lab scale we have tried all 4 of biochars available commercial in India, and out of those the bamboo results is only being shown. However, we have data for all the other things, and Government of India has published a very good document of what are the biochars available and can be tried. But we have concentrated here on bamboo itself because of its sustainable benefit in Indian tropical conditions. First of all, we have tried from 0% to 100% of utilization ratio with a replacement with a factor of 10% intervals. And as we can see that the productivity is at a peak level of around 30 to 40% of replacement level, beyond which the productivity gets reduced because of its strength deterioration and breakage tendencies. Next, coming to the tumbler index, which is strength of the measurement of strength in Sinter for actual blast furnace condition. The higher, the better. The plateau comes at around 20 to 40% range, beyond which it is deteriorated in a very large extent and not recommended with a conventional process. But however, there are other processes currently under development stage so that we can utilize more of a biochar. Next is the granulometry stage. This comes directly from the mean size figure. That means our requirement is 5 to 40 millimeters typically for the blast furnace, and we have done a good comparison of coke versus biochar, because ultimately we have the mandated to replace coke breeze, not fully, but up to what much of percentage we could. And again, our standard ratio of lab scale was around 20 to 30%. With these data, we have moved to our plant to validate this lab scale data into an industrial scale and to see what are the benefits we can achieve. Now, this is the emission potential, theoretical emission potential of different biochar substitution vis-a-vis original coke breeze. There was a large concern for us as well as for steel makers that biochar is having a higher VM. Definitely is a higher VM, while coke breeze is having a VM of around 0.8 to 1%, whereas biochar is having what we have chosen, 7 to 8%, not max 10%. Which can be a very good potential challenge. So we have projected different values of biochar replacement vis-a-vis the volatile matter, obvious kg per ton of Sinter, which will ultimately go into the ESPN, process ESPN and other installations, and NOx and SOx emission in various conditions. And we can see that the more biochar additions, the more benefit we'll get in emission terms. But again, my conditions will, from the production and productivity angle, is also considered. So all this data, we have tried for an optimization of having a lower value of productivity, however, having a much benefit of emission potential. So our main study was an industrial optimization. Now the plant scale trial, we have conducted a plant scale trial in Durgapur steel plant in a full-fledged trial, and these were the before going for an industrial scale. We have tested some physical analysis of these properties of flowability and then bulk density and then other properties for handling of these biochars, because what this Hausner ratio and Carr ratio and then flowability test, that's all these standards, because our systems were designed for handling coke breeze, and biochar is having some some properties different from that of coke breeze. So we had to suitably modify our charging devices, our wave feeders, our measurement devices to suit the percentage replacement of biochar. These were the how we have charged the coke breeze, and this is the bamboo biochar we have sourced. As you can see that the main characteristics is the visual differences is this. It is having a finer as well as bigger particle mixture, slightly moist, and also tends to be a bit sticky in nature. These all considerations we have taken care in our charging devices. And this trial has been continuously done from February to June this year. And the trial result, these are industrial trial results. We can show that the tumbler index and both the Sinter granulometry has been benefited from these biochar additions because of its higher temperature generations and a low flame front generation, and the tumbler index and AI and AM. AM is the short form of arithmetic mean size, which is requirement of blast furnace for a very good blast furnace operation and reducing the instability. And AI is a measurement of Sinter superfines generation, which is also an emission criteria. We had to maintain a lower AI for a better environment. And this is a unique study we have conducted. We have lifted a fully ready pellet with biochar and as well as without biochar, and compared these two pellets with a side-by-side and size analysis. And these we have segregated this into 9 compartments, both horizontally as well as across the width of the machine. And the result of this granulometry, Sinter granulometry, that is the what percentage of 45 to 40 minus 5 mm from each layer has been compared with biochar and without biochar. So from the value, we can see that the top layer, which is weaker because of its thermal shock and thermal insufficiency, heat insufficiency, it has been partially solved with the biochar additions. And these figures, these figures has ultimately been effective in having a good blast furnace grade sinter generation at Durgapur Steel Plant. Now, through this industrial trial, we could reduce the 2 to 2.5 kg TGS of CO2, which is of coke breeze, which ultimately corresponds to a figure of 8.5 kg CO2 and 0.01 TCO2 per TCS in industrial scale. And improvement in productivity as well as sinter quality has been achieved in a plant scale. And not limited to that, this is a very encouraging trend, and not limiting ourselves to this encouraging trend, we are planning to go much further in both lab scale as well as in industrial continuous basis. And this is the one snapshot of the resultant discussions in terms of calorific value, in terms of reducibility, strength, and from the angle of practical applications such as the storage and handling, which we have felt and we have solved because of out of our designing aspects. We have jotted it down. And we are not limiting to this. We have planned to move further with a lab scale and plant scale, which will be concluded here.
Thank you, Mr. Dhara, for explaining the technical part what you have researched in your laboratory, and followed by its application in the plant scale trial. So we have found that biochar can replace coke bridge by say 20 to 30%. To achieve desired sinter quality, which can be utilized in blast furnace. But by saying that, then we have to find, we have done that experiment, or we have done that trial, so that it is now decided that biochar is a replacement of coke bridge partially. So after that, what will be the roadmap for its sustainability? Now, for getting biochar, say in 1 acre of land, we can produce say 20 to 30 ton of bamboo in the first. It is a fast growing grass type of plant. So in 1 acre of land, we can get in the preliminary years, that is say 3 to 4 years, so we can get 20 to 30 ton of bamboo. After a maturity of say 7 to 8 years or 9 years or so, its productivity or the yield of bamboo per acre of land will be increased by say 40 to 50 ton. But to start with, we have to find that how much biochar can be extracted from the bamboos. Now the result says that it is a yield say 20%, 20 to 30%. That means if we want to get 1 ton of biochar, we will have to produce 5 ton of bamboo. So it will take, or it will require a huge land to get the biochar utilized in sinter plant application to replace coke bridge. Now where do I find that huge land? Basically, and what will be the cost of that production of biochar? So that is the some of the questions it will be coming up. Now we can use that degraded lands or abandoned mines or barren lands where farming is not possible, infertile lands, that is basically wastage, and their human population, particularly in India, and there is a question of their sustainability, question of their employment. So we can use that abandoned or degraded lands for creation of green cover through this bamboo cultivation, so that we can have this biochar from those land, and it will somehow form a circular economy out of that. We can use that land, we can form bamboo, and we can give employment to the local people, and we can uplift that poorer class of India. So that is the circular economy to be formed. We are in talks of some interested parties all over the India, and we will be using an expression of interest to form and to collaborate with our company, so that we can have biochar from that company, and we can make steel greener. Now, to talk about that India's main the thought process or roadmap, what India is thinking right now. So far we have perceived that is India is the first country to define green steel taxonomy in terms of carbon dioxide equivalent emission. India has defined that the carbon dioxide equivalent emission of 2.2 ton per ton of finished steel will be termed as green steel. So there is different category of green steel in India right now. That is, the green steel will be declared if the carbon dioxide equivalent emission is 2.2 ton per ton of finished steel, and that will be categorized as 3-star. That organization or company producing by emitting that much carbon dioxide. And for 4-star category, it is less than 2 ton carbon dioxide equivalent per ton of finished steel, and for 5 ton, it is less than 1.6 ton. Yeah. So, and India, further going ahead, it has signed fossil fuel non-proliferation treaty. So it is one of the 143 countries all over the world. And in the Viksit Bharat, that is we have declared steel as the backbone of infrastructure development. So that is all, and I would like to thank World Steel for giving us the opportunity to showcase our effort towards the fight towards climate control. And we can say that here the technology providers are developing through different research, the different kind of weapon to fight climate control, and we are here to implement or carry your weapon to fight for that reason. So thank you very much.
From the floor? I see one here.
Yeah.
Just wait for a microphone, we'll come to you.
Hello, hello. Yeah, technically, it is convincible that we can use biochar as a replacement of coke breeze. How about the concern of deforestation? If we use the bamboos for making the biochar, then there is a concern of deforestation also. How we can address that?
In India, basically, bamboo has been declared grass plant, that is a species of grass. So this grass species doesn't come under forest policy. So there is no problem of cutting of bamboo, which is prohibited under the forest policy of deforestation. So in that purpose, India government has declared this bamboo as is a grass species of plant. So there will be no legal issues of cutting of bamboo, which can go against that deforestation.
Okay, I think there's one more. Thomas?
Can you tell us more about the industrial production of the biochar? How do you realize this biochar production on an industrial basis?
Pardon, can you please repeat?
Can you tell us more regarding the technological process for the bamboo biochar production? Which pyrolysis process do you use?
You are talking about, whatever I get, that you are talking about the pyrolysis process.
Yes, how you realize this? How big will the plant?
Yes, yes.
Which technology do you use?
For technology, there are mainly two types can be categorized. That is, one is pyrolysis and another is that gasification, basically. So one pyrolysis machines are there available in India. Some farms are using to get biochar out of this pyrolysis process. And as well as some gasification plant is also there, where they used to use chimneys and that some sort of kiln where they can directly burn in absence of air. So in pyrolysis process, the benefit of this thing, we can have that syngas out of that bamboo biochar. The volatile matter converts into the syngas. That syngas can be utilized as a resource of energy. And ultimately, if you use pyrolysis machine, then you can have biochar and you can have syngas. And that syngas simultaneously will be helping in producing biochar. So if you run a pyrolysis machine, then the expenditure or the additional usage of fuel will be very less. So when you use pyrolysis machine, you can get biochar, you can get syngas, and such a voluminous quantity of syngas we can be having that from pyrolysis machine. We can sell the syngas to for some power generation purpose. So pyrolysis machine will be the best suited.
Thank you.
Thank you. Thank you.
Thank you very much, Mr. Majumdar. Our next presentation, another shift of gear. I'd like to welcome Dr. David KEARNS to the stage. David is the country manager for Australia and New Zealand at the Global Carbon Capture and Storage Institute. David's role is to help drive progress in CCS development across Australia, New Zealand. He works with industry and other potential industries where CCS can be used. So please, David, you have 20 minutes. The floor is yours.
Right. Thank you very much, Andrew, and thank you to World Steel Association for the opportunity to speak here today. Just a little bit about the Global CCS Institute for those of you who have not heard of us. We are an international CCS think tank headquartered in Melbourne, Australia, with offices all over the world. Really, we're an organisation about advocating for CCS as part of the solution to climate change. We have over 200 members amongst governments, technology companies, emitters, and NGOs. And we do a lot of work around advocacy for CCS, as well as producing thought leadership publications. If you go to our website, you'll find a whole lot of publications there. And knowledge sharing at events like today. So very pleased to be here and to talk about CCS for steelmaking. Just quickly, the plan for today, looking at the need for CCS in the global steel sector. We've heard about a lot of other decarbonisation approaches. Wanted to outline the case. A quick overview for those of you who are not so familiar with the types of CO2 capture technologies that are available, how the costs behave, looking at CCS as a pathway to lower cost clean hydrogen for those of you who are interested in using hydrogen for steelmaking, a review of some of the CCS projects in the iron and steel facilities at the moment, as well as a few case studies of projects. At a glance, what is CCS? Carbon capture and storage involves 3 key steps, the first being CO2 capture. Capture is a gas separation process where we take CO2 that is dilute and often at low pressure, and we actually separate that CO2 into a high purity form. The reason we do this is that subsequently we're planning to store it geologically, and we need to have it at high concentration to make sure we make the most of those subsurface volumes that we have. The second part is transport, where we move it to its ultimate destination. We do that, there's 2 primary means. One is pipelines, where it's sent by high pressure, so we pressurize the CO2 and pipe it. The other is we can chill it down to low temperatures and liquefy it. That happens at sort of low to moderate pressures, and that's suitable for global shipping. And there is already a substantial amount of infrastructure globally for both modes, and we're seeing a lot more CO2 shipping emerging at the moment. Finally is storage. We won't talk about storage so much today, but ultimately it's putting it into the ground, into formations, porous formations under the ground, very similar to those that hold natural gas and oil naturally. So today's focus is going to be primarily on capturing CO2 because that's the part that is directly impacting steelmaking. But you do need to realise, of course, there's going to be transport and storage downstream. So why would we want to look at CCS? Well, if you look at the steel industry globally, We have a range of average ages of steel plants around the world, but what you can see according to this graph here from the IEA, there's a very, very large section of global steel plants that are relatively young. In fact, if you look at China, the average age of a steel plant in China is under 20 years, well below the typical age of retirement for a steel-making facility. And for that reason, we need good retrofitting options for decarbonising these plants. It is very unlikely these plants are just going to be scrapped and replaced with newer technologies. We need to have abundant options to retrofit them. One of those options that is available, and the technology is available today, is carbon capture and storage. One of the other things that CCS is also useful for is for making low-carbon hydrogen. We did have some of our speakers earlier talking about using SMR or ATR. I'll briefly touch on that as well. Having a look at some of the different types of CO2 capture technology, they're all doing the same thing. They're all separating CO2 from a mixture of gases at high purity and then producing it at high purity. The predominant form of CO2 capture technology today is based on solvents. So solvents are liquids which interact with a mixture of gases and preferentially absorb CO2 from the gas. We can then separate and remove that CO2 from the solvent later on. The typical solvents that we use, the most common ones are based on what are called amines. So amines are a class of chemicals. The way that we get the CO2 back out of the solvent is that we typically use heat. So we heat the solvent back up, and then it releases the CO2 in a high purity form. So that's how we achieve our separation. I mentioned amines are the most common. We also have hot potassium carbonate as another variant. And there is an incredible amount of technology development underway by companies around the world to find new and improved versions of these solvents. Amines work really well. They've been around for a long time, but they do have some downsides. They're fairly energy intensive to regenerate, to get that CO2 back out, that heat step. And so we're always looking for better ways to do that. We also have what are called physical solvents, which don't involve a chemical reaction. They just simply absorb CO2 the way that you would have CO2 absorbed, say, in a fizzy drink. They tend to be better for higher pressure applications, not so relevant for steel making, but I just mentioned those for completeness. To give you a sense of costs, this is a result from a study that we did a few years ago at the Institute, looking at what we call benchmark costs of CO2 capture. These are based on MEA, which is one of the amine solvents. And I say benchmark costs because they don't include any of the extras. So it's assuming that your source gas is relatively clean. What you have along the x-axis here is what's known as the partial pressure CO2. So that's essentially the fraction of CO2 in that flue gas multiplied by the overall gas pressure. And so as you go to the right, it's becoming more and more concentrated in CO2. And you can see a fairly obvious relationship of cost, which is on the y-axis, that if you've got dilute CO2, it's more expensive per tonne to capture. As you've got more concentrated, the costs come down. The other thing that you see on here are the bars. The bars represent scale. So the bottom end of the bar represents a higher scale. The top end of the bar represents a smaller scale. Steel making tends to sort of fit within sort of the middle third just to the right of that. And so we typically get those sort of range of costs, but as you'll see in a moment, there are other factors to consider. A few of the other capture technologies, a key one is adsorbents, so ad with a D, not ab with a B. Adsorbents are solid porous materials that have binding sites on them that preferentially take up CO2 from a gas. They're very effective, they've been around for a long time. They have a very large surface area, so you can get a lot of binding sites into a very small amount of space. And we can use chemical or physical binding mechanisms to actually absorb CO2 preferentially from a gas. There's a few different processes involved to using them. The main ones are known as temperature swing adsorption, TSA, vacuum swing adsorption, or pressure swing adsorption, PSA, or some combination. Sometimes we use a combination of pressure and temperature swings. Membranes are another capture technology. They're a semi-permeable membrane, effectively acting like a fancy microscopic nanoscopic filter that will preferentially let CO2 go through at a different rate to the other gases in the gas stream. And so you can concentrate up the gas with CO2 in it. That process is primarily driven by pressure, so it's pressure forcing the gas through the membrane. And another category that's getting more attention these days is cryogenic CO2 capture. Cryogenic capture essentially involves condensing CO2 out of a gas stream by making it very cold. So typically CO2 is going to come out of the, as you cool the gas down, is going to condense early. So once you've removed the water, that is. Once you're getting down to sort of minus 30, minus 40 degrees, the CO2 will condense and you can just separate it as a liquid. These processes, they work, they're certainly effective. They're not quite so relevant for steelmaking, except if you're getting involved in certain sort of supplying industries. And just to round out the picture, these are probably a little bit less relevant for steelmaking. We also have what are known as oxy-combustion capture. This is where rather than combusting a fuel in air, we combust it in purified oxygen. We produce high-purity CO2 directly from the combustion. We don't have a mix of gases. So we make sure that the nitrogen that would normally be polluting or contaminating your flue gas is not present. There's also chemical looping, which uses a chemical intermediate and effectively means that you are kind of keeping you're keeping the fuel and the combustion reactions kind of separated. We don't see too many of those, but they are gaining a place. So stepping out of there, what are we looking at in terms of technology? So when we're looking to select a CO2 technology for a particular application, I've already mentioned to you that CO2 concentration really matters. Now, in the case of steelmaking, your concentrations tend to be set by the process itself, but those of you who are looking to develop new and improved forms of iron and steelmaking, anything you can do to produce a higher purity CO2 stream will be very, very effective at bringing down the cost of capture downstream of that. Scale matters. Higher scale tends to be cheaper than lower scale. And then we've got factors like what's the pressure of the stream. Low pressure streams tend to be common in steelmaking. Cooling requirements, so most CO2 capture processes require cooling. How much capture you're doing, so whether you want to capture 90, 95, 98, 99% of the CO2. And the last one, which is particularly relevant for steelmaking, is impurities. So stream impurities, including particulates, other chemicals and so on. These can have a very direct bearing on the technology that you might choose. Some technologies are more tolerant of impurities than others. I'll very briefly touch on hydrogen, but we've had some very good presentations on that already. I simply wanted to make the point here that one of the ways that CCS can help steelmaking is in helping to produce reasonably priced hydrogen for the use in your processes. I've mentioned here a few different approaches. There's a range of costs in the charts there. I won't go into those in detail. But I will simply make the point that if you use either steam methane reforming, SMR, or autothermal reforming, ATR, with CCS, you can get considerably lower cost hydrogen at scale compared to electrolysis-based hydrogen. At least that's the situation at the moment. And so we see this as a really important step for enabling hydrogen-based steel making at a reasonable price. Cost matters. We don't have the time or the luxury of time to wait for electrolysis-based hydrogen to come down the cost curve. And so this lets you get started with your hydrogen-based steel making today. If and when the electrolysis-based hydrogen can step in later on, then it's simply a matter of swapping out your source of hydrogen. This is a list of some of the commercial CCS projects in the steel sector around the world. I've highlighted there in orange the ADNOC El Rieda Emirates Steel capture process. That's been operating since 2016 on a commercial basis. That's in Abu Dhabi. That facility captures CO2 and ultimately uses it for enhanced oil recovery. So they're injected into the ground, but it helps to push oil out of the ground. That's the commercial basis for that project. We've also got the Baotou Steel project in China. That is very close to operation from what I've been able to obtain in the media. Both of those are solvent-based capture processes, so they're using solvents to capture CO2 from steel plants. The ADNOC facility is a DRI unit. Baotou Steel is a blast furnace unit. And so that actually makes the Baotou Steel unit particularly important because of its scale in terms of being, going to be the largest blast furnace unit with CCS in the world. Range of other projects going on around the world in advanced development, which by our terminology means in a feed study, or early development, which means it's undergoing feasibility. And so we're hoping to see more of these projects come online as the incentives and the economics become possible. In terms of where CCS fits within facilities, I've got an example here of where we could see it fitting in for blast furnace-based facilities. One of the things that really characterises steel plants compared to other places where you might use CCS is that you don't have one or two flue gas sources, you actually have many of them. It actually shares this feature in common with oil refineries. These are the two industries that kind of have lots of point sources spread out geographically over a site. And for that reason, you actually usually need to have separate capture units for each point source. Unless they're very close together and you can aggregate them, you would normally have to have separate capture on each of them. There's some typical CO2 ranges for the different sources, point sources that you would get. And as I showed you on that chart before, you would get different cost impacts of those. So the more concentrated ones, like the hot stoves, for example, you would expect to be a little bit lower cost for capture than some of the others. I'll also make the point that in many facilities, the blast furnace gas is used as a fuel for making power. If you're doing that, you tend to get more concentrated CO2 than if you burn a more conventional fuel for power generation. So that's kind of favourable for CO2 capture from that as well. So we typically would see that if you've got over about 15% CO2, that's really a good opportunity for capture. Here are some example projects. I'll go through a few that are blast furnace based and then a few that are DRI based. These are some, I guess, what you would say larger demonstration projects, high profile demonstrations. The DMX demonstration in Dunkirk in France is a really important one. It's using a solvent, or it's testing a new solvent by Axens. It's a biphasic solvent. What a biphasic solvent is a solvent that actually turns into two immiscible liquids, which you can then separate off. It's very, very good for energy efficiency in terms of the regeneration of the solvent, so you can reuse it. It's about a 4,400 tonne capacity, so it's not intended for commercial use, it's intended for testing. Steelmaking in Belgium is a carbon capture and utilisation project, so up until now I've been talking about carbon capture and storage. Carbon capture and utilisation is another where you take the CO2 that you capture and you utilise it for some economic purpose. That's using LanzaTech's process, which we did hear mentioned earlier today. And also MHI, Mitsubishi Heavy Industry, a very key sort of company in carbon capture around the world. They've got a project in Belgium, which they're trialling for 2 years, so that trial is underway at the moment, which is looking at blast furnace off gases and hot strip mill reheating furnace gases. So that's in Ghent in Belgium. And some examples from DRI, I've mentioned the Abu Dhabi example, the Abu Dhabi Carbon Capture Company, which is operating off gas coming off the Emirates Steel facility. That's a DRI unit. That's 800,000 tonnes per annum capacity. It's producing 98% pure CO2, so decent purity. That's been operating since 2016 and is a really good example, and for quite a long time now has been really the primary example of CCS in steel making. And also there's the example of CCU, carbon capture and utilisation, at the Ternium Puebla facility in Mexico. Doesn't get as much profile because it's for utilisation purposes, but that's actually quite large. That's capturing 1.7 million tonnes per annum of CO2, and it's been running for longer as well, so it's a good example of one of those plants. It captures CO2 for the merchant market, so CO2 is used for things like food production, greenhouses and all that sort of thing. That's the sort of application that it's used for. That's the end of my presentation. Thank you very much, and I'll be happy to take some questions.
Thanks, David. That's a great overview. Do we have any questions from the floor on all things CCS? My question is really about impurities. I mean, steel plants are generally regulated on their air emissions. It varies, mostly by site. I think China is probably the tightest. Do the capture technologies generally, can they cope with the current degree of sort of gas cleaning that we have to do, or are we likely to need extra processing on the flue gases?
You would typically see carbon capture facilities installed downstream of existing gas cleaning equipment because we want to deal with things like the particulates ahead of time if we can. we see a pretty wide tolerance of variation in those gas streams because we know that the CO2 concentration won't be constant. We know that the flows might not be constant either. And so that's something that the designs have to take account of. I will say that the solvent-based processes are a little bit more flexible in that regard, that they can tolerate those variations a little bit more.
Yeah, I could imagine membranes would be quite difficult in terms of particulates, right?
Yeah. I mean, I mentioned membranes. I think they're an important process. They're probably not going to take the front of the row as far as the steelmaking facilities are concerned. I expect to predominantly see solvents.
Makes sense. We have a question here, if we get a microphone.
Yeah, good afternoon, sir. This is S. Dhara from Steel Authority of India Limited. Sir, blast furnace, what we have shown that blast furnace CCS project is okay because concentration of CO is much higher. But first time I'm seeing that hot steel mill off-gas carbon capture. How much feasible is this? Because the CO concentration is very less, I think, it will be.
So, and this is where it's useful to maybe give you the examples of carbon capture being done in other industries where it does get more dilute.
Specifically about this reheating furnaces off-gas carbon capture of this, because blast furnace off-gas carbon capture is a established or common process, but hot strip mill off-gas coming from hot strip mill off-gas, the carbon percentage is very low. So how much of potential or how much of utilization in this field? First question. And if hot strip mill off-gas is possible for CCS reduction, then there is a scope of ample CCS in other processes also.
So we've seen carbon capture technologies suitable for down to 1% CO2 in some cases. So for aluminium smelters, they go down to about 1%. So we can go, technically we can go very dilute. That's rarely the barrier. The barrier is usually economic. So the more dilute you go, the more expensive the capture will be. And so what we tend to expect is that the more concentrated sources, they're the lower hanging fruit. They're the ones that will happen first. Whereas you would expect the less concentrated sources might be picked up later on in subsequent projects. And in fact, that's one of the things that we've been recommending to some of the companies we've been working with, is that if you are developing CCS at a steel facility where you've got lots of point sources that are sort of spread out, that you also build kind of with the future in mind, say the internal pipe work that might be on the site to gather the CO2, that you consider that, well, okay, you know you're going to be building a certain amount of capacity today, but maybe in a few years you'll be building some more, so make sure that you've got kind of that all plotted out and planned ahead of time. But technologically, yeah, we can go very, very dilute if need be. It's really just a question of cost. Thank you.
Thank you, David.
Thank you.
Okay, we'll move on. Our next speaker is ready. Excellent. Please come up. Shimura-san, you're very welcome. Mr. Shimura is a researcher at JFE Corporation, Japan, obviously, where he's working on the development of decarbonized steelmaking. Relatively new to JFE, you joined the company just 2 years ago. He's working in the carbon neutral process research department, and he's going to be talking to us today about the development of carbon recycling, direct reduction process using methanation. So, Shimura-san, the floor is yours. You have 20 minutes.
Thank you for your information. I'm Yasumitsu SHIMURA from JFE Steel. JFE Steel Corporation in Japan. And today I will talk about this topic. Outline of today's presentation is shown here. First, I explain about the background of this study. This slide shows JFE Steel transition strategy to low carbon process. We consider the period up to 2030 to be a transition period, and we promote the transition to low carbon steel process. The period to 2030 to 2050 is defined as the innovation period. We aim to achieve carbon neutrality by establishing and implement innovation technologies. We aim to reduce carbon dioxide emission by 30% or more in 2030. And next, in 2050, we aim for carbon neutrality. The following technologies will be developed to achieve these challenging goals, such as use of conventional blast furnace method combined with carbon neutral process, expand the use of electric furnace, and increase the amount of scrap used. And today I will explain about this direct reaction process. In this slide, the two figures of the left respond to the concept of the conventional iron making process, the blast furnace method, and the direct reaction method. We are trying to incorporate a carbon recycling process into these conventional iron making process. And the target are carbon in the blast furnace, in the blast method, and carbon in the top gas of the shaft furnace in the direct reaction method. As introduced the period presentations, JFE Steel is proposing a carbon recycling blast furnace that captures carbon dioxide from the blast furnace top gas, synthesizes methane, and injects it into the blast furnace again. Carbon is recycled. Similarly, we now propose a carbon recycling shaft furnace, combining carbon recycling process with a conventional direct reduction method. And the following slide explains the concept of this process. Next, I will explain the outline of proposed carbon recycling shaft furnace. JFE Steel plans to develop carbon recycling direct reduction steelmaking. The diagram on the right shows outline of the carbon recycled shaft furnace. The features of this process are first, indirect use of hydrogen through methanation. And second, circulation of carbon within the process and overcoming the endothermic effects of hydrogen reduction. In this process, methane is obtained by reacting carbon oxide and carbon dioxide in the top gas with green hydrogen. The regenerated methane is injected into the furnace or reformed into carbon oxide and hydrogen before being blown into the furnace. Carbon is not discharged out of the system and circulates in the system. Hydrogen is supplied from the outside and only water is discharged out of the system. As you know, reduction with hydrogen is a highly endothermic reaction. But in this process, carbon is not discharged out of the system. Carbon continues to remain in the reduction gas as carbon monoxide. There is no need to increase the hydrogen ratio in the reducing gas. The aim of the carbon recycling is first to achieve carbon neutrality by repeatedly reusing carbon. Since reduction by carbon oxide is an endothermic reaction, it is considered possible to avoid the endothermic effect of hydrogen reduction, such as decrease in reaction rate or degradation of iron pellets. And this is explained on the next slide. And this slide shows the effect of increasing the hydrogen ratio in the reducing gas on the distribution of the reduction degree in the shaft furnace. And this is an example of numerical simulation, the reaction behavior in the furnace. And the combustion of the reducing gas is assumed of hydrogen and carbon oxide ratio of 1.7 and 3.7. The center figures shows calculated distribution of reduction degrees. In this example, it is shown that the reduction in the reactor is delayed by increasing the hydrogen ratio. The reduction degree in the center is lower, and this becomes more significant when the hydrogen content in the reducing gas increases. And by increasing the hydrogen ratio in the reduction gas, the low reducing area is explained and expanded and upper part of the furnace. And because reducing degradation occurs in the lower reduction regions, it is assumed that reduction degradation is likely to occur when the hydrogen concentration increases. For these reactions, we through that endothermic reaction should be avoided as much as possible. This slide describes the various subjects of endothermic reactions. As I have said many times before, reduction by hydrogen involves a large endothermal and reaction rate will decrease, and there is a concern that lowering of the reaction rate will cause decrease in productivity of shaft furnace. Also, as I mentioned before, there is a concern that the decrease in temperature with endothermal may promote the reduction degradation of iron ore pellets. In this photograph, the reduction was carried out under the condition of hydrogen and carbon oxide of form 4. And the tumbling test was performed on the sample after the reaction. As you can see, the strength of the reduction sample decreased and a fine powder is generated. It is expanded that the use of low-grade pellets will increase in the future. We think that low-grade pellets are likely to occur reduction degradation. If this process with the hydrogen ratio in the reducing gas does not increase, it is through that it is possible to minimize the occurrence of reduction degradation. Next, the test plan for methanation will be explained. This page outlines the proposed methanation test experiment. Methanation is a reaction of carbon oxide or carbon monoxide with hydrogen using a catalyst to form CH4 and water. Methanation is recognized as one of the important carbon CCU technologies for achieving carbon neutrality in Japan. Methanation consists of these two reactions. Reaction of carbon dioxide with hydrogen or carbon oxide with hydrogen, both in exothermic reaction. So gas cooling is required. Recovery of waste heat generated by the reaction is also important. After the production of methane, the moisture in the gas is removed by cooling. This slide introduced concerns regarding methanation using carbon oxide and carbon monoxide mixed gas. The images on the left shows the temperature distribution inside a reactor calculated using 2D methanation model when methanation reaction occurs without carbon oxide. A peak is present at the reactor inlet, and it is said that if the temperature in this area is too high, the catalyst inside will detonate. The blue line in the graph on the right is an example of the temperature distribution when a methanation reaction occurred using only carbon dioxide and hydrogen. It is known that methanation reaction from carbon oxide produce more heat and have a faster reaction rate than methanation reaction from carbon dioxide. From this reaction, it is expected that the temperature distribution will be as shown by the red line when methanation is performed using shaft furnace top gas. And furthermore, because the shaft furnace process handles extremely large amount of gas, we believe that currently commercially available reactors cannot be used as is. For this reason, we are currently investigating both lab-scale methanation tests using simulated gas and temperature distribution calculation using a methanation model. Finally, I explained about concentration construction plan for experiment shaft furnace. In 2024, JFE Steel constructed a small shaft furnace approximately 30 meters high, as shown in the photo, and on a site approximately 50 meters by 50 meters. A gas supply system for hydrogen and neutral gas, as well as a reformer, installed near the small shaft furnace, enabling using to freely adjust the ratio of carbon monoxide and hydrogen in the reduction furnace. Operation began at the end of 2024, and we have successfully produced DRI constantly using low-grade pellets and 100% hydrogen. We will continue to identify optimal reduction constructions for each property of low-grade raw materials, primarily using blast furnace grade pellets. And we also continue to develop direct reduction method using carbon recycling technology. Finally, this slide outlines the summary of presentation. JFE Steel's plan to develop carbon recycling direct reduction steelmaking. In order to establish a carbon recycle shaft furnace process, we plan to investigate the effect of gas composition and hydrogen water addition amount of methanation reaction efficiency. We have been conducting reduction tests since the end of 2024 using a small shaft furnace built within our own factory. That's all. Thank you.
Thank you, Shimura-san. Do we have any questions? We do. We can get a microphone.
Thank you for your presentation. And my understanding is that your process to use the CO2 and the green hydrogen to produce the methane. And my question is that if you have the green hydrogen, and why don't you use the green hydrogen as the reducing gas to reduce the payload? And why do you want to produce the methane?
Sorry.
Okay,
one
I
more.
repeat my question.
Okay.
And my question is that if you have the green hydrogen, and why don't you use the green hydrogen as a reducing gas for the reduction? And why do you want to combine the green hydrogen and the CO2 to produce the methane, and the methane will be used as a reducing gas for the reduction?
This is difficult. This is difficult question to answer.
Maybe you could take it up at the coffee break in that case. Okay. Thank you for your presentation.
Thank you.
Okay, we are almost at the coffee break. We have one more presentation before you can recaffeinate. So I would like to invite, I don't need to invite, Filippo, you're here already. So I would like to introduce, in that case, Filippo CIRILLI from RINA Consulting, working in RINA, currently holding the position in decarbonization and energy transition, and you're going to talk to us today about the HYDRA project, the largest project in Italy that covers the decarbonization of the entire steel production process. Fantastic. You have 20 minutes. You're keeping us from our coffee, so please be efficient, but we can't wait to hear your presentation. Thank you.
Ladies and gentlemen, good afternoon, and thank you, Mr. Chairman, for your kind introduction. It's the last presentation of this session, so I'll do my best to keep to capture your attention. And my speech will be about our presentation for the decarbonization of steelmaking route. I will give you a very, very quick overview of the company and the general context in which we are moving, but we know it very well, and then I will go through the process and what I call the highlights, so which are, in my opinion, in our opinion, in the opinion of our company, the main issues which should be studied with a so large experimental platform. RINA Group is a large international group with a presence all over the world, and it has a long history. The history of RINA started with the unification of Italy and is continuing right now, and outlined that 12 years ago RINA acquired a company, my company, that is now the name is RINA Consulting Centro Sviluppo Materiali, which means RINA Consulting Materials Research Center. We were the research center of the public Italian steelmaking. Then we became private, and now we are more or less 250 employees. Most of them are researchers. Our headquarters is in Rome. And why this project? We started working in the frame of European funded project. We have seen also a good presentation today by Mr. Klaus Peters about the support of the European Union for the decarbonization. This scheme is taken from one of these projects, Green Steel for Europe, and we decided to perform a large project to support the decarbonization, and we worked actively in this project, analyzing the technologies, the readiness, the technological readiness level, and so on, and we decided to focus our attention on the technologies which was, let's say, already available on the market, but ready for the transition to hydrogen, but with several aspects which needs to be further studied as an R&D center for the full hydrogen implementation. For sure, there are other technologies. All are interesting from my point of view, but this was the selection, the choice that we did. And so, as I said, the process is for the process development, and so we is not focused on the development of the plant. So we made our selection from what we consider the state of the art. So the provider of the plant is Tenova, and the plant, the DRP plant, but I will give you more insight in a few slides, is based on the Energyron technology. So Tenova is the provider that we selected. Danieli is in charge of the direction of the pilot facilities, and Sapio is the gas company. And what we did first, before starting the project, we started discussing with steelmakers, and we in parallel with the analysis of the technologies, and we recognized that a single pilot plant was not enough to support those type of transition. It was necessary a complete platform. A complete platform faces the issues of hydrogen utilization, considering all the aspects, from the material and components qualification and testing, up to the utilization for direct reduction process and further melting step. We selected the electrical furnace, but I will give you some more insight in a few slides. And also considering the downstream processes, we also had some very interesting presentation before mine. So downstream is also very natural gas consuming step, and so it deserves an important attention. So our pilot facility is, or let's say our project is divided into 4 streams of activity. We addressed as work packages, one for the labs, one for the erection of a direct reduction plant, another one for the electrical furnace, and finally the ones devoted to the study of combustion issues. So the first work package is devoted to the realization of labs for the qualification of materials and components. We already have those type of facilities in my company, but we decided to strongly improve those testing capability for several reasons. Here I listed some main ones. So to define guidelines and procedures for the use of materials, to give confidence about the steelmakers, about the performances and the utilization of materials and components, to evaluate the impact of atmosphere, of hydrogen containing atmosphere, so I mean pure hydrogen and also blends of hydrogen and natural gas on the material or the performances of the materials, and also to give supports for deeper knowledge and also upgrade the existing standards. You know that there is a lack of a standard regulation related to hydrogen utilization at industrial level. The second work package is direction of the DRP plant, so the plant for the direct reduction of iron ore pellets. And as I said, this plant is based on Energyron technology, and it is provided by Tenova. The productivity of this plant is 100 kilograms per hour, so more or less 2,002 tons per day. In this moment, the plant it will be fed by 4 wagon tanks. 4 wagon tanks, not only to ensure, let's say, a certain enough time for testing, but also to perform gas blending. That is very important for those type of activities. The plant is equipped also with the gas and water treatment lines, and also with the CO2 capture unit based on mine. The electrical furnace is a furnace of a 7-ton capacity, and it has 2 interesting characteristics. It is equipped with a lance which can act as hydrogen burner, and it is also equipped with injectors able to inject, let me say, standard materials, so I mean pulverized coal, but also secondary carbon carriers, which means in practice biochar, polymers, rubber grinds, or whatever contains carbon and can be used as alternative materials to fossil utilization in electrical furnace. various purposes for carburization of the bus, foaming, and so on. Finally, the fourth work packages did not require new facilities because we already have a combustion station in the north of Italy in which we can test burners up to 3 megawatt of power. And we have also lab furnaces to simulate the hydrogen combustion atmosphere and to test the impact of hydrogen combustion atmospheres on different steel grades as a function of time and temperature, and also performing the scaling and pickling test to evaluate also the impact on the capability of scale removal. Just a very quick geographical information. We are in Italy and we are located in Rome. And these are our working sites. You see the labs are almost completed, and the DRP plant also is almost installed. And yesterday we had also an official visit of representatives of Italian governments. The electrical furnace is installed, and the first heat with our electrical furnace is foreseen within December. So I don't know if we are trying to run as much as possible. So I don't know if just before Christmas or just after Christmas, but we will switch on the furnace. And we are also erecting our training center, because dissemination and training activities are important part of this project. So the project started 2 years ago, and now we are in the middle of the project. We are completing the erection of plant and labs, and we expect that the full operativity of our platform will be after the commissionings and training of technicians will be, I think, in spring of 2026. In the meanwhile, we started some preliminary activities. So we performed, for example, a very interesting activity about the kinetic of reduction of low and high quality grade pellets, and we have seen that there is a different impact of some controlling parameters. Here you can see the kinetic curves of we reported the mass loss. We may report the metallization degree, and we have also those curves, but with the mass loss, the different behavior of the two grades is, I think, more impressive. So in case of high grade, we recognize that the kinetic is enhanced, and there is a less dispersion of data respect to the variability of process parameters. We performed a lot of tests to determine the impact of water at a different temperature on the oxidation rate. We performed experiments from 900 degrees up to 12,000 of degrees at a different temperature and with the different steel grades. And we are also, we're just starting an activity to study the compatibility and the limits of existing combustion system working in blends with hydrogen and natural gas. We started also a cooperation with the universities. 3 graduated theses are ongoing, and new ones are going to start. And we are also starting engagement with other European projects to enable synergies, spillover, and the exchange of experience, and also interaction with industrial partners. For us, it's essential to discuss continually with the steel makers in order to, let's say, listen which are the needs for a proper designing of the experimental metrics. What I call highlights. So what are, in our opinion, the main features which could and should be studied with such an experimental facilities? One, we have learned very well in the previous presentations, is related to the quality of the iron ore. We know that the availability of high-grade pellets is not so high, and more or less the foreseen amount of those materials will remain the same, at least in the next 5 years. So I'm pretty confident that we are not able to work with very, very low quality, but we think that maybe we can enlarge a little bit, or let's say we can enlarge the range of acceptability of DRI pellets working on the melting step. When I say working on the melting step, I mean proper slag management. So for us, there's slag composition, but also the refractory composition is not a religious dogma. So we are working in this moment with the support of calculation code, but once the facility will be ready, we are going to test also with our experimental facility how we can better manage, if it's possible, the process accordingly to the amount of gang that is present in the DRI. And another aspect is the blending with the scrap. That is the other aspect which we can modify in order to accept also low-grade materials. And another aspect is the hydrogen availability. From this bar graph, you can see that the green hydrogen production capability is expected to grow according to the studies, for example, of the International Energy Agency. But if you go into details, you see that a lot of projects are, let's say, at the early stage, are at the level of feasibility, are under examination. So this means that the future situation in the next few years is not yet well defined, and the best countermeasure is to be able to work in a flexible manner, which means able to be working and able to be changing the operating parameters and the operating practices when the availability of reducing gases is not exactly constant and can be variable with time. Another important issue is the carbonization of DRI. So if you produce with hydrogen, you don't have absolutely, for sure, carbon into your direct reduced iron. Is this a good or negative fact? There are a lot of analysis about this aspect. Personally, I'm not so sure that a DRI totally carbon-free is the best option for the melting step. So the carbonization, or the way in which we may face the issue of carbonization of DRI, is an important matter. Basically, we can provide carbon to the process in different manners, as a solid carbon in the mix of pellets, or injected into the electrical furnace, or as a gaseous carbon blended with hydrogen or injected in the lower part of the furnace. So, and which is the best optimization practice, or let's say the best options? I would say it depends on the steel that we are going to produce, but in any case, some more insights can be obtained performing tailored experimental campaign. An important aspect which I would like to outline is the fact that the reducing step and the melting step has to be considered jointly. So when you perform an overall analysis of your process from the energetic point of view, from the material consumption and so on, the two processes has to be considered jointly, because in a lot of situations, what is the best for the reduction step is the worst for the melting step. So if you obtain DRI with a lower metallization degree, it's just a very basic example, you will consume less energy and less gas in the reducing step, but you will consume more energy into the electrical furnace. So you need to understand which is the break-even. That is not always the same for all the production, for all the type of production. And in this sense, I think that the possibility to have an experimental facilities and also modeling fine-tuned in order to give those type of response are essential to manage those type of issues. And then at the end, the impact on the materials. So the impact of hydrogen on the materials, not only on steels, in general metals and polymers and composite materials is a well-known issue in the scientific world. But now we are going to, let's say, put the material in a more severe conditions, so more studies are necessary, and this is the reason why we imagine that those type of facility without advanced labs is not complete. So this is the reason why we decide to invest really strongly also in basic studies of materials interaction. This is another example about materials focused on refractories, which is the impact of hydrogen or water on the refractory durability. Here we performed some tests with magnesia refractory for the ladle. In this case, the topic was about ladle preheating, and in this case we see that at the ladle preheating temperature there is an interaction, but it is meaningful from the practical point of view, but those type of study should be also repeated for other types of refractory. For the moment, we don't have yet the experimental facility, so we perform simulation with the calculation code, making some hypotheses about the interaction. So we have some reaction scheme in our mind, and we have to check by experimental activities. At the end, further possibility of the experimental facility. Here you can see the border of our project and the border of, let's say, important surrounding processes that are the hydrogen production. Here I put a drawing simulating an electrolyzer, but hydrogen can be produced with different technologies, so also the analysis of different production technologies is an issue. The interaction with the grid of the renewable energy is an important issue for sure, and there are some important aspects which are not explicitly included in our project, but on which we are already starting working. That is the development of innovative monitoring and control system. For example, we are making some hypothesis of working with innovative system form of gas analysis or for the monitoring of the gaseous atmosphere inside the DRP reactor. Another interesting topic from my point of view is also the flexible management of the CO2 capture unit, because if we work in a flexible manner, which means different blends of hydrogen and natural gas, also the fine-tuning of a CO2 capture system is a new issue, because you are experiencing variable amount of CO2 in your gaseous streams, and the development of innovative sensors and control technologies, and also the testing, for example, of new plant components of materials. I mentioned refractory. We have some hypotheses, so we are thinking to put just some bricks of innovative refractories in the electrical furnace to perform some experimental campaigns and to take samples to check what happened. I explain in a very simple way, but you know, experimental activity is a little bit more complex, but this is the basic concept. So, as conclusion, I will send a very short clip. The duration is 1 minute. What's happening? Sorry, I was pushing the wrong button. Once again, maybe? Yeah.
Steel is essential to our daily lives, but its production is one of the main sources of CO2 emissions. For every ton of steel produced, nearly 2 tons of CO2 are released into the atmosphere. The challenge is to decarbonize steel without losing market competitiveness. HYDRA ET06, promoted by RINA and funded under the IPCEI, High 2 Use Initiative, with support from the European Commission and the Italian Ministry of Enterprises and Made in Italy, proves that it is possible to produce green steel using hybrid hydrogen-methane systems and other reducing gases. In Castel Romano, near Rome, we are building a pilot steel plant where we test new technologies: a hydrogen-ready direct reduction reactor, an electric furnace that produces steel using the pre-reduced material from the reactor, and advanced laboratories to test materials and components in hydrogen-rich atmospheres. HYDRA is not just technology, it's a true innovation ecosystem where training, research, and collaboration between industry and young talents come together to spread expertise and strengthen future collaborations. HYDRA results will be transferable to all industrial sectors worldwide, yielding breakthrough productive processes while contributing to a greener, more sustainable future. HYDRA is the concrete demonstration that steel decarbonization with hydrogen is possible.
So, thank you very much. Sorry for the extra minute.
Thank you. Do we have any questions, Joachim? Can we get a microphone here, just behind you?
Oh, there. Thank you, Filippo. More of a comment. You talked about refractory. I can just say that in those installations we made in full scale that have been running like Govaco for almost 2 years, they have not seen any negative impact on the refractory from running with 100% oxygen, 100% hydrogen. So good if you can tell us why there is no negative impact, but in the full scale, they haven't seen any negative impact on the refractory. And the discussions with the refractory suppliers said that they didn't expect that, but if there was any issue, we have solutions for it. But there wasn't, actually. But maybe you can explain it from your tests also. But I wanted to share that that's good news, actually.
This is good to know. When we perform an experimental activity, it's not necessary we are expecting negative results. So when we have positive results, it's the best. Yeah, exactly. In this case, the test was performed on MgO carbon refractories and we tested both the slag lining and the steel lining. Maybe you are, and we do not observe significant impact at 900 degrees. I think you are referring to refractories overheating furnaces.
Yes, yeah, I wanted to qualify. I talk about ladles and reheat furnaces, not about the EAF. Yes, that's correct.
Yeah, and okay, and so thanks for the information. Maybe we can share some more data, but if this is the evidence, we can focus the experiments on other topics. But what I can say is that an important aspect is what we are going to, let's say, to test is that in any case the effect of parameters. So, for example, we performed the test at 900 degrees. We see an interaction, what is negligible from the practical point of view. And now what we are going to perform is the same test at higher temperature, not only for academic curiosity, but to study if there is a strong impact on temperature, which means if there is a strong impact on local peak temperature. But it does not mean that necessarily there must be an effect.
Okay, thank you, Filippo. Great presentation.
Thank you.
Okay, we are perfectly on time, so thank you to all of our presenters. We are now going to take a coffee break.